Hello guys, and welcome in this new recording. Today we continue with the second part of the GPU reduction overview that we started last time. If you remember, last time we just provided an overview on the naive implementation for this reduction process and the first three NVIDIA reduction kernels which are available in this paper. So kernel number 2 and kernel number 3. So we just stopped here. So starting from there, the first issue that would be discussed here is the fact that when you are performing the reduction operation with the kernel version 3, you have half of the thread in the first step that are actually not used. So they're only really used to copy the data from the GPU memory, so the device memory. I made actually a small drawing concerning this. It's basically what's happening here. If you assume that you have only 8 threads per work group, so in fact you rather have 32 threads per work group, but that's a simple drawing. So let's just say we have 8 threads. What's happening is the first 4 threads are going to copy the first 4 values, then the last 4 threads are going to copy those 4 last value for each work group, and that's all the work that there is for those 4 threads, because after that only the first 4 threads are going to be used, and they're going to perform the first addition operation to update the content of those 4 slots using the 8 values together. So if you think about that, one way to optimize this could be to, well, discard those 4 threads completely, and you would then consider that you can build an array with only 4 slots. You don't really need this part anymore, and you could do the first addition directly. So the first thread here would read 2 values from the device memory, this one and this one, and it would add them together before storing the result in the shared memory. So that's one way of seeing the situation, so the improvement that you can make. You could reduce the size of your work group by 2, but you can in fact see that from a different perspective. You could say instead that you're actually not going to reduce the size of your work group. You keep the size of the work group to what it is. So in this small demonstration it's 8, but in fact I think I mentioned that already, in the actual WebGPU shader that we're using, the maximum size we can use is 256, so that's what we're actually using. And so when you keep this value, then you also keep your shared memory size to the same value, so 8 in this case. And what you're going to do instead is you're not going to retrieve only 8 values, but instead you're going to retrieve 16 values. So those first 8 values just here plus the next 8 values, and you're going to perform the first addition operation just before again writing anything for the first time into the shared memory array. So yeah, what's really different here is that when you're building your workgroup grid, you're going to divide the grid size by 2, because you have twice less workgroup to use to process the same number of input elements. And okay, so that's what I can show you in the shader that we have written for that. Actually, I can show you that here in the unit test. So the shader 4, when you call the reduction function here, you see that there is an additional parameter now, the reduc factor, which is set to 2. And for this function, the default value is in fact 1. And we're going to use that just here when it's time to compute the grid size, so the number of work group that you want to execute on the x-axis at least. So you're going to compute that as usual, and then you divide that by the reduction factor. Keep in mind that here we have an integer division, so no floating point or anything like that playing around. And this is it for this version 4. Apart from that, you see that the code here, the only change that we have is here. We're going to retrieve 2 values from the input buffer, add them together, and only after that write the first value in the shared memory. Okay, so this is what is discussed here also in the NVIDIA paper. This is how you're going to do the addition in CUDA, and you can expect this to provide you a significant performance boost. And I think I've noted that here. The output that we get is pretty efficient, so 418 gigabyte per second, while for the version 3 I think we had 200 and something, 216 gigabyte per second, almost twice as fast, so pretty good. Okay, so now let's move to the reduction kernel version 5. Okay, so for this one the idea was to unroll the last warp. So what does it mean exactly? In case you don't know that, the threads that are executed on the GPU are executed by a warp, and the warp is usually 32 threads on NVIDIA GPUs at least, and those threads are executed with the SIM protocol, so single instruction multiple data, which means that they are always synchronous. They are always executing exactly the same instruction, so there's no way they could get out of synchronization, but only those 32 threads. What's happening for us is that we have a shared array. You can imagine this is a view on a part of this shared array, which is going to be 256 slots, and this is going to be processed by chunks of 32 slots. In fact, you could have a few warp executing at the same time on the GPU, but I think usually it's something like between 2 and 4. Not quite sure exactly, but they are not synchronized between them. And the thing is, you want to have all the data in the shared memory available for one step of your computation before you can move to the next step. Because to compute the data here, you will need those inputs, but you would also need to add the inputs from the third chunk in this drawing. And for this, it's the same thing. You will need this part of the input, and you also need this part. So you really need to synchronize everything before you can move to the next step. And this is true up to a given point, because at some point you will reach the case where what you're going to execute here only contains 32 threads. So for this one, you have your 32 threads. So they're going to copy the data from here and add that. And when this is done, for the next step, what should you do? You actually don't need to have a synchronization here, because those 32 threads, they are anyway synchronized. So everything is written already in this part of the shared memory. There's no way it could be otherwise. And so that means that from this step, you actually don't need to synchronize anymore, and you could perform the computation without the call to the sync thread or workgroup bar here in our case. So that's what was discussed here. First, there's a discussion on the result that was achieved with kernel 4, which is still pretty far from the maximum value. And next, yes, we have this discussion on why we don't really need to synchronize when we have less than 32 threads to execute. And then, yes, we're going to introduce this function, this warp reduce function, and we're going to stop when the size that we have remaining is 32 elements. If this is the case, then we are going to break outside of the loop, and then we just figure out if the thread ID that we have is less than 32, and if it is, we execute this warp reduce function. So let's see on our side what we did exactly. It's pretty much the same thing. I have re-implemented this warp reduce function, and now when we do the for loop, we're going to stop when s is 32, and we're going to check then if the thread ID is less than 32 to execute this function. So this is it, and that's going to provide you again a pretty significant boost of the performances, which is going in the same direction as what was explained here in the paper. Okay, so after that we have a suggestion to do a complete unrolling, except that when you're working with CUDA you can use templates to do that. So if you use a template implementation of your function here, you can specify the block size as a template parameter, and this would be resolved at compilation time. So it means that, as discussed here in the paper, everything which is in red here is going to be evaluated at compilation time, so it's going to be removed from the shader computation itself, which is going to help, of course, to improve the final performances. Another thing that we have to keep in mind here is for CUDA, you can have up to 512 threads per work group, and I'm not even sure this is still true. It could be that now we're more like at 1024. I'm not sure anymore about that. But anyway, in WebGPU, we're still limited to 256 threads per work group at max. So this is what we're going to use for our own implementation. And so let's see the Reduction shader version 6. What we have here is the unwrapping of the for loop. In fact, there were only 2 steps left in this for loop, because when the value here is defined, it means that the workgroup size is 256, and so you would perform this first part to check if your thread ID is less than 128, and you do the computation in this case. And then the next step is only this one, and after that you're going to reach directly the case where you need to execute the warp reduce function. For the warp reduce function, I just introduced those preprocessor definition to try to mimic the idea that we have in the paper, which is to use those template parameters, so the block size template parameters. But in fact, it's not really useful in my case, because I'm going to use in anyway always a block size of 256. All of those preprocessor definition would be defined in my case. Okay, and after that we are going to move to the final kernel version, which is version number 7. And there's a discussion here on how you could try to improve further the performances, and the result of that is really what we have here. The idea that each thread should actually handle more inputs than what we're using by default, so the simple inputs of 256, because you're supposed to do some computation in the threads and also some distribution of the work, but there's some kind of compromise between those two perspectives. You have to not handle all the elements in a single thread at the end, because that would be inefficient. Handling a single element per thread is also less efficient. So in the middle between those two, there is a value which is more appropriate to use. And in fact, this is a bit similar in design to what we're doing in the kernel number 4. So the idea is really to extend a bit further on this. In the kernel number 4, if you remember, we were using 8 inputs plus 8 input in one thread. So we were adding those two together before writing the first value in the shared memory. So the idea here is, why stop at using only 2 values? You could just as well use 1, 2, 3, 4 values together, or you could use 8 values together, or 16 values together. And if you do that, well, you're going to improve the performances again. So for instance, here I'm going to get 711 gigabyte per second, which is pretty amazing if you remember the maximum bandwidth, which is 936 gigabyte per second on the GPU that I'm using right now. So pretty good, and I'm very happy with those results, in fact. So let's have a look at the kernel version 7. What do? We have introduced this those additional definition, preprocessor definitions, and this is just to indicate that, okay, if this one is defined, it means I want to sum 2 values from the inputs together before writing something to the shared memory. If this one is defined, we had 2 more values, so that's 4 values at the same time. In this case, we had 4 more values, so we have 8 of them now. And now for the last one, we add again 8 additional values, so that's a total of 16 values together, which are added before writing the result in the shared memory. And yeah, apart from that, we keep the for loop unrolled. Here in the reduce in the warp reduce function was still doing the same thing. As I said, all of those preprocessors are always defined in my case, and that's it. So we can have a look maybe at how those are implemented in the unit test. So we specify here that the reduction factor is going to be 16 this time. We're processing 16 elements per thread, and we also provide those additional preprocessor definitions. And so yeah, this is it. With this, guys, we can run maybe just quickly the reduction unit test so you can see by yourself. So these are the results that we get from the first one to the last one. So that's the kernel version 7, version 6. Well, you see here that version 5 was apparently faster, but this is actually changing from time to time, and usually you still have the proper order. Here you have it, even though if they are pretty close both together. I think this is all I wanted to mention concerning this reduction algorithm. We have also covered everything here on the paper. We reached the reduction version 7, performing multiple addition per thread, and that's the final result that we get. Okay, great. So yeah, this is it for this time. Thank you for watching. As usual, if you have any question on this and you think I may answer, yeah, just let me know in the comments. And otherwise, I'll see you next time. Bye bye.